Well, thank you, John. And what I have here is a project area that we've had for quite some time in northern Chile. And it's about, I think, 15, 20 kilometers north of Collahuasi and Quebrada Blanca to really nice porphyry systems. And it's kind of on the end of the trail there. You know, you go further north and you pick up another belt. You pick up this Eocene belt that has a different orientation than the north-south alignment along the west fissure. And part of the reason why we do ZTEM for porphyry exploration dates back to something we did in 2007. Rich Lavelle, who was our president or head of exploration at the time, had heard about this ZTEM approach, which at that time was licensed to the exploration syndicate. They had the rights on it, and they wanted some places to fly in Arizona. And so we figured we'd do a case study flying over in the Safford area over our Lone Star deposit, which is currently, we're doing quite a bit of drilling and it's being stripped. It's the biggest deposit in the Saffard District, and it has deep oxidation in the center, which goes down to about 3,000 feet. And it's about, I forget the exact grade, it's 2.4 billion tons at like 0.42%. And it's surrounded by sulfide. There's good sulfide mineralization that goes really deep there. So it looked like a good test area to do this. Problem is there's a lot of culture in the area. So this is where the ZTEM survey was flown. We couldn't go over Dos Pobres, San Juan area where the pit was starting because too much infrastructure, power lines, etc. And so we flew, and the orientation on this were lines in this direction. And I can't remember offhand the spacing. I think it was,
Sorry, Ken.
I don't know if it was 200 meters, I think it was, but
Yeah.
thank you. So the results of that were this. I had taken a bunch of historic data from the late 60s, early 70s, combination of Phelps Dodge data and Kennecott data, IP data, and it had it all input by Zong and modeled. And so when we got the ZTEM data, you know, they were giving us these DT plots, and they weren't doing all the inversions and stuff at that time. So I just took the lowest DT plot, which I think was 28 hertz at the time, figured, okay, resistivity, which I kind of knew from this stuff over here, the resistivity generated from the IP survey, is around 100 ohm meters. So I just used the skin depth equation, figured out that this had to be about on the same level as the 600 meter elevation slice. And as you can see, these guys are really beautiful agreement between the two. So I sent this as a slide to Rich Lavelle, and next thing I knew, we flew about $1 million worth of ZTEM over Arizona and areas where we had a mine or prospective areas around it. And so that's kind of how we got into using ZTEM a lot. And then, so that's why I was flown down here in Chile. Chile has a lot of problems with doing geophysical surveys. Real resistive cover from the Atacama, Caliche, all sorts of stuff. So the ZTEM, you know, because it's a pretty resistive surface does a good job of mapping there. In this case, our project area is up here, and there's a combination of gravels and this ignimbrite unit, which is the resistivity of that is probably over 1,000 ohm meters. So they applied, they did a ZTEM survey over the whole block, and the main thing was to see beneath that cover. Also, the complicating the situation is underneath that ignimbrite cover, there's gravels that get saline water in. So you've got this contrast of a very resistive layer, very conductive layer, and then the basement. We've hit this property with about everything you could think of. We've done a whole series of IP with the GDAS system out of Southern Rock Geophysics, which gave us pole-dipole resistivity and IP, and at the same time MT data. There's older stuff done. There were some TEM lines done. There was spectrum data taken over in this part of the block. So we had a lot of data, and my job was kind of pull all this together, write up a report, make sense of it, mainly with the hopes of understanding the geology a little better, and then targeting on the basis of the IP. So these are the lines that we got at the time. We got Geotech to do inversion on 3 or 4 lines. These were the pertinent lines where we had MT data and DC resistivity from the IP. So we'll be comparing those lines. And so from the IP and the MT, we got really good mapping of the ignimbrite and also of the conductive gravels beneath. And with the ZTEM, we were able to invert a ZTEM to see more or less the interface of the combination of the ignimbrite and the conductive gravels with basement. We couldn't discriminate that conductive gravel there. So the main thing we're looking at is what's going on in the basement, and the ZTEM did a good job of that by comparison to the MT. So here is one of the northernmost line, and what I put in here, this is essentially, this is the ignimbrite on the top, okay? And then this is where the conductive gravels, this is the interface with the basement here. And as you can see, that interface is picked pretty well here, and there is suggestion of that gravel layer in here. It doesn't go real low like it does on both the MT and the DC resistivity. Actually, with the DC resistivity from the IP lines, where this contact is not on the other side of this really conductive feature, but almost through the center of it. And that's on the basis of drill holes. And so this is the second line, and you can see the real strength of ZTEM in picking vertical interfaces, because these interfaces are shown very well on both the IP-DC resistivity and the MT2D conversion. And you go up and you can pick breaks that you're seeing up in the ZTEM data. So it's a good way to maybe look at your fault mapping in the basement. And not only for the fault mapping, but we're picking up these conductive features down the basement, which may be of interest. And you can see that the 2D inversion and the ZTEM are picking pretty much the same zones. There's different shapes and everything else. But if you just had the ZTEM data and were looking for a conductive feature, you know, you wouldn't be too far off if you picked one of these as comparison to what you're seeing on the MT. Now here, this one line, this is the northernmost line, able to have the DC resistivity from the whole dipole survey. That's the chargeability there, which didn't help us much for anything. And here's the MT2D. This, the last thing we did out there was we did a vector IP survey using multiple transmitters and just kind of a grid laid out with all the dipoles and MT soundings. And this was the model out of that vector IP. And as you can see, you don't really pick up the conductive layer in this thing. But the similarity to what you're getting out of the ZTEM inversion is, I think, really a compelling case for saying that the ZTEM is giving us a pretty good idea of the resistivity structure in the basement. And so this was my interpretation of one of the 1D inversions. I like the MT1D inversion. This was done with Zong software, inversion software, is that you can pick up more breaks. The 2D tends to smooth things. It's great for looking at layers, but the 1D really helps pick up some of these breaks, which I could correlate with some other things. The interesting thing you get in on this line is most of the other lines you went through the conductive gravel layer and then you went into the resistivity went up, but it was still pretty low resistivity. On two of these lines to the south, we start picking up this other higher resistivity layer. So I don't know exactly what that is. You have different rocks on either the west side of this whole area, which is the Collahuasi formation, which makes a lot of andesitic units, probably higher resistivity. And way over on the west side, you've got Cretaceous sediments, sandstones and siltstones, probably more conductive. But I don't know what it means in this case, but it is picking up this other layer on a couple of lines. And so this is that same line, and just comparing the 1D with the 2D, and then with the ZTEM inversion here. And again, you can see these same features are being pulled out in the ZTEM inversion versus ZTEM.
ZTEM is fine.
And this was type of stuff I like to do is, you know, a lot of geologists and, well, either way, geologists, geophysicists, they see this stuff and they go like, ah. So, and then geophysicists don't want to put any geology on things, but I don't care, you know. Why not try and do something with the data that makes some sense? And so by doing this, I could see that the basement has probably got a whole series of faults, and that you may have like step faulting within this overall graben. You may have like a kind of piston faulting, as they call it, or other things happening down in the basement, which will affect where you're going to want to explore. Now, it'd be nice if we had deep enough IP to see a response in some of that stuff, but we didn't. Then my simple approach, when we were first getting all the ZTEM data back in 2008 and that time, was just take the higher frequency stuff and just use that as essentially my resistivity mapping and go through and look for breaks and interpret some fault structures. Some of these faults I knew that this was a big major fault here and that there were some faults over here. The problem was in this middle area here where the west fissure is coming through, there was no good definition on this is a lower frequency, and then what I like to do to see do these things that I get on the higher frequency correlate with what I'm seeing down lower frequency. And actually, by the shift in them, I calculated a dip for this fault. You can do that, and it was about 70 degrees, which where I saw a measurement somewhere is pretty close to what it actually is. And then saw this thing like this horse block in here of more resistant material in there. And then this kind of circular feature up here. And this was essentially the analytic signal didn't do much better than I just took the reduced to the equator magnetics and did an inverted color scale on it to point out the magnetic, well, they're lows, but would actually be the highs and reduced to the pole. And I can't see much fabric coming through here defining the the west fissure zone. Well, I did something that Sergio Vieira, our geophysicist down in Brazil, hates to see me do down at that latitude, which is reduced to the pole. But when I reduced to the pole, you can see this whole series, and the west fissure isn't just one strand, it's multiple strands coming up here. And I thought it made a real good case in conjunction with what I saw from the two different frequencies of the ZTEM to make a good case that it is reflected beneath this cover, which is, and actually up in the cover you can see little displacements in the ignimbrite that are subtle. So, and then this was the gravity. So I took all these things together to try to get an integrated geologic idea of what's going on here. Now, did it help us find anything? No. The IP was kind of a red herring in a few places, but there's still an IP target out there which we haven't drilled. We had a JV with a partner, and he picked to drill the last kind of go-around, and the hole got lost. There were a bunch of problems, and it wasn't where the best IP response was. So it's still perspective, but I think we have a better understanding of the underlying geology and what's going on in this area. Thanks.
Do we have any questions? Harish?
Yeah, Mark, that first case study at Saffard District, how much was the volcanic tertiary cover over there?
It can be about 150 to 200. The combined thickness with the gravels is about almost all the way across there, about 300 to 350 meters. The ignimbrite is probably up to about 200 meters, and it's extensive across the way. Coming down to the south, you start losing some of that cover, and you're picking up just the gravels, and the gravels are thickening down on that end.
Okay.
Jerry?
Mark, I applaud your courage in tackling collectively some pretty tough exploration areas, sectors in known districts. When you go back to your early initial work, you commented on the Saffard District. The example you showed could be interpreted in somewhat other manner. Did you sort of look at your $1 million invested or $1 million in ZTEM, again, after you'd sort of revisited, from your Chile experience, and what observations would you place
Yeah.
there?
We had all the Arizona ZTEM stuff modeled by somebody in this room, which did a good job of giving us cross-sectional and 3D models. And the problem was, for a while, I was kind of out of commission as my role as bastard geophysicist in our organization, because I was working in the mine site stuff, and I was just running drill projects and doing geology. And when I got back with the greenfields, I was asked more and more to do geophysical stuff. And I think that we need to go back and take a look at all that data that we have. And now we've got somebody who is really capable of doing that. We hired Carlos Azara last June. He started with us, and that's one of the things that are in the works, to go back through that data and get the maximum value out of it. Why it worked in the Safford District is partly due to some earlier work by Phelps Dodge Chief Geophysicist Tony Hawk. And he looked at the Safford District with a thing, how can you tell where you've got good oxide mineralization? Because there's not a lot of enrichment in the Safford District. It's mostly oxidation. And so he looked at the resistivity characteristics. Where you get oxidation, your resistivity goes way back up. And I think that's why it worked over Lone Star, because the fact of that deep oxidation in the middle, and sulfide's pretty close on the flanks of it, and that provided that resistivity contrast. So the main thing is looking for these circular elliptical features, but whether or not they're going to have that resistive core and more conductive outer ring, that's the question. It has a lot to do with geology, has a lot to do with structure. Given the same geology, I would think how I look at it as a geologist is, if you have that potassic core with case bar veining, flooding, silica, you're going to have more resistive material than you're going to have out in the phyllic zone. And the phyllic's going to have interconnected pyrite veins along with all the phyllosilicates, which bring resistivity way down. So that's kind of the model I use in looking at a lot of the data. And I like looking, like I say, at the lower frequency, and then see if it persists all the way up. I think maybe that's a near surface thing, and it's being propagated down. And then I use it with the mag and go through and see other mag features where I'm finding these features. It's a pretty simplistic way of going about it, and so far I haven't found anything like that, but I got some ideas. Thank you.
More questions? Yes, Ken.
In your Chilean example, you had some Horst and Graben situations, and we've been seeing some interest in, not that the electrical techniques, both airborne and ground, can be very, very compelling, but looking at passive seismic to basically try and assist in mapping in those situations. Can you comment at all about whether Freeport has thought about that, or tried these, or cross-compared?
Yeah, we have actually. Probably many of you may know or not know, but we picked up a big block just south of Calama called the Ricardo block. And we are trying to, there's been a lot of drilling in the past there, but it's right on the West Fissure. The West Fissure goes right through the Calama airport. And we're south of the airport there. And we're looking for something close to that. And that was brought up of trying to use passive seismics in that environment. And actually you use, potentially use a blast from Chuquicamata. I think it's something that definitely needs to be applied. The other thing is, I went to a geochem short course last weekend with Peter Winterburn, and one of his students, Alexander Brown, he has been did some work down near Kalama, where they're looking at seismic pumping of features that penetrate up over this post-mineral cover, and looking at the geochemistry right along these fractures. So that's another thing that could be applied, and looking at something like this going, say, hey, because you're getting essentially, not necessarily copper, but you're getting this whole other suite of elements that are precipitating out in these little zones along these fractures.
Any other questions? Well, we're just, I would love to ask more questions for you. It's always interesting. We don't have the opportunity to hear you enough. I want to